Some 4.5 billion years ago, the solar system was a giant game of cosmic pinball. During those early ages, a planetary body the size of Mars slammed into the still forming Earth. The collision was so powerful, it broke apart that impacting protoplanet, nicknamed Theia, and sent huge amounts of material into orbit around Earth, material that eventually coalesced into the Moon. A new study suggests that during this impact, Theia left some of its material at the surface of the still forming Earth, and that debris sank into our planet. Published in the journal Nature, the study finds that today, material from Theia may account for two enormous, dense chunks in Earth's mantle. Earth scientists have known for decades that continent-sized blobs of denser material exist toward the base of the mantle near the boundary with the core. This new study uses simulations of the Moon forming impact, as well as the evolution of Earth's interior to address where the impactor's leftovers may be hiding, and how they may have changed over time. It would mean that we have material that can tell us more about Theia and help us better understand the Moon forming impact. Like an onion, Earth's interior is composed of layers. Unlike the vegetable, however, our planet's core is hot, dense, and mostly metallic, made of an outer rotating molten layer surrounding a denser 1,500-mile wide ball. Outside of these two core layers is the huge mantle, which makes up more than 80% of our planet's volume. Atop the mantle is the crust, the surface. The mantle is where much of the action takes place. Continental plates shift and collide, and magma oozes. It's also difficult to access directly due to its depth, so to better understand the mantle, researchers measure how seismic waves travel through it during earthquakes. As those waves pass through materials of different densities, they change velocity or direction. By piecing together those bits of information, researchers can essentially map the inside of our planet. Such studies over the past few decades have shown two enormous blobs in the lower portions of the mantle, one under South Africa and another under the Pacific Ocean, that differ in density and composition from the surrounding material. Seismic waves slow when they pass through these blobs, and so geoscientists have dubbed them large low-shear-velocity provinces, LLSVPs. These regions are denser than the rest of the mantle, and they seem to have been around for billions of years. Scientists aren't sure, however, how these LLSVP blobs came to be within the mantle. Perhaps the new study suggests those clumps came from the protoplanet that smashed into Earth, leading to the Moon's formation. When the impactor Theia hit Earth 4.5 billion years ago, it broke apart, and clouds of molten debris and vapor surrounded Earth, congregating to form the Moon. In the past 50 years, scientists have studied lunar samples collected during the Apollo missions and from meteorite falls, and combined that information with computer simulations to piece together this story, the leading theory for how the Moon formed. But there are still some questions about this theory, including one that, why haven't we found remnants of Theia here on Earth? Researchers focused on simulating the collision between Theia and proto-Earth and how the material would mix or not mix within Earth's layers. Their computer model included finer details than previous simulations, revealing some of the Theia material that melted during the collision remained on Earth. The model suggests that material was denser than the upper mantle of proto-Earth and sank into the lower mantle, where it has remained as identifiable blobs, never mixing. The biggest question about the new model is whether material from the impact could avoid being mixed and homogenized into the Earth's mantle over the next 4.5 billion years. Some researchers aren't convinced. In their simulations, the mantle of Theia and Earth's mantle tend to be well mixed. Scientists agree these dense regions in Earth's mantle have existed for a long time, but exactly how long and where they came from is still up for debate. There is an alternative explanation for the formation of these piles. Researchers point toward evidence that much of what is now solid mantle had been hot magma early in Earth's evolution, prior to separating into the current layers. The upper layer solidified quickly as it radiated heat into space. The lower layer, however, solidified slowly and thus had time to differentiate into denser blobs and less dense areas. The next step is to compare the chemical signatures of material from these blobs and from the Moon, which is made mostly of Theia. If they have the same geochemical signature, they must originate from the same planet. But gathering new material to study is easier said than done. Geoscientists can't drill deep enough into Earth to directly sample the blobs, although rock from the deep interior sometimes reaches the surface, such as ocean island basalts. The Moon's surface has been exposed to billions of years of space, weathering, and may be contaminated by meteorites. So researchers would like to analyze material from the lunar mantle as well. But the samples scientists have in Earth's laboratories are mostly from the surface. New pieces of the Moon might have to wait until a sample return mission to the southern region, where the mantle is more exposed and accessible. Until then, scientists will continue to refine their models to look for the ghost of Theia. Thank you for watching. If you've enjoyed our videos, subscribe to our channel for there's more to come.